Hi, my name is Ashish Kashyap, and in this podcast, I want to take you on a journey through science and together explore the amazing stories of discovery and genius through which we understand our world today. We start off with the most fundamental of topics. So, what do you understand by the words space and time? Perhaps you picture space as the blackness between the stars as you turn your gaze towards the sky on a cold winter's night. Time may be the tick of your watch. We all have an intuitive feel for space and time. They are part of the fabric of our existence. We move through space on the surface of our blue planet as time ticks by. During the late years of the 19th century, a series of scientific breakthroughs in apparently unrelated fields began to force physicists to re examine these simple and intuitive pictures of space and time. In order to understand Einstein's special theory of relativity, the theory that introduced the world to that most famous of all equations, E is equal to mc square, we must try and grasp the meaning of the symbol c, which is the speed of light. Einstein's theory is at its heart a description of space and time. Central to the theory is the notion of a special speed, a speed beyond which nothing in the universe, no matter how powerful, can accelerate. This speed is the speed of light, 299,792,458 meters per second in the vacuum of empty space. Traveling at this speed, a flash of light beamed out from Earth takes 8 minutes to pass by the sun. 100,000 years to cross our own Milky Way galaxy, and over 2 million years to reach our nearest galactic neighbor Andromeda. Tonight, the largest telescopes on Earth will gaze outward into the blackness of space and capture ancient light from distant, long dead suns at the edge of the observable universe. This light began its journey over 10 billion years ago, several billion years before the Earth was formed from a collapsing cloud of interstellar dust. The speed of light is fast, amazingly fast, but nowhere near infinitely fast. When faced with the great distances between stars and the galaxies, light speed can be frustratingly slow. Slow enough that we can accelerate very small objects to within a fraction of a percent of the speed of light with machines like the 27-kilometer long Large Hadron Collider at the European Centre for Particle Physics, or CERN, in Switzerland. The existence of such a special speed, a cosmic speed limit, is a strange concept. It has a much deeper role to play in Einstein's universe, and there is a good reason why light travels at the speed it does. We will get to that later on. For now, it is sufficient to say that when objects approach the special speed, strange things can happen. How else could an object be prevented from accelerating beyond that speed? It is as though there was a universal law of physics that prevented your car going faster than 70 kilometers per hour, no matter how large the engine. Unlike a speed restriction, however, this law is not something that needs to be enforced by some external agency, maybe a police force. The very fabric of space and time is constructed in such a way that it is absolutely impossible to break the law. And this turns out to be extremely fortunate, for otherwise, there would be unpleasant consequences. Later, we shall see that if it were possible to exceed the speed of light, we could construct time machines capable of transporting us backward through history to any point in the past. We could even imagine journeying back to a time before we were born, which leads to all sorts of nasty paradoxes. So space and time are delicately interwoven in a way that prevents such paradoxes from occurring. However, there is a price to pay. We must abandon our deeply held notions of space and time. Einstein's universe is one in which moving clocks will tick slowly, moving objects will shrink, and we can journey billions of years into the future. It is a universe in which a human lifetime can be stretched almost indefinitely. We could watch the sun die, we could see the Earth's oceans boil away, and our solar system be plunged into perpetual night. We could watch the birth of stars from swirling dust clouds, the formation of planets, and maybe the origins of life on new, as yet unformed worlds. Einstein's universe allows us to journey into the far future while keeping the doors to the past firmly locked behind us. We will see how Einstein was forced to come up with such a fantastical picture of our universe and how this picture has been shown to be correct in many scientific experiments and technological applications. In fact, the satellite navigation system in your car, for example, is designed to account for the fact that time ticks at a different rate on the orbiting satellites than it does on the ground. Einstein's picture is radical. Space and time are not what they seem. But we are getting a little ahead of ourselves at this stage. To understand and appreciate Einstein's radical discovery, we must first think very carefully about the two concepts that are at the heart of relativity theory: space and time. Imagine you are reading a book while riding on an aircraft. At 12 p.m., you glance at your watch, decide to put your book down, leave your seat, and walk down the aisle to chat with your friend 10 rows in front of you. At 12:15, you return to your seat, sit down, and pick up your book. Common sense tells us that you have returned to the same place. You had to walk the same 10 rows to get back to your seat, and when you returned, your book was where you left it. Now, think a little more deeply about the concept of the same place. Thinking carefully about these apparently obvious concepts will lead us in the footsteps of Aristotle, Galileo Galilei, Newton, and Einstein. How then could we go about defining precisely what we mean by the same place? We already know how to do this on the surface of the Earth. A globe has a set of grid lines, lines of latitude and lines of longitude drawn onto its surface. Any place on the Earth's surface can be described by two numbers representing the position on this grid. Therefore, by simple analogy, one way to pin down the location of any point, whether on the Earth's surface or not, would be to picture an imaginary three-dimensional grid extending upward from the Earth's surface and into the air. In fact, the grid could also carry on downward through to the center of the Earth. We could then describe where everything in the world sits relative to the grid, whether in the air, on the surface, or below ground. In fact, we need not stop with just the world. The grid could extend outward beyond the moon, past Jupiter, Neptune, and Pluto, beyond even the edge of the Milky Way galaxy to the farthest reaches of the universe. Given our giant, possibly infinitely large grid, we can work out where everything is. Our grid, therefore, defines an arena within which everything exists, a kind of giant box containing all the objects in the universe. We may even be tempted to call this giant arena space. Let's get back to the question of what is meant by the same place and return to the aircraft example. You might suppose that at 12 p.m. and at 12:15 p.m., you were at the same point in space. Now imagine what the sequence of events looks like to a person sitting on the ground watching the plane. If she sees the plane fly overhead at 600 kilometers per hour, she would say that between 12 and 12:15 you had moved 150 kilometers. In other words, you were at different points in space at 12 and at 12:15 p.m. Who is correct? Who has moved and who has stood still? If you cannot see the answer to this apparently simple question, then you are in good company. Aristotle, one of the greatest minds of ancient Greece, got it dead wrong. Aristotle would have answered unequivocally that it is you, the passenger on the aircraft, who is moving. He believed that the earth stands still at the center of the universe. The sun, the moon, planets, and stars rotate around the earth. He therefore shared our intuitively satisfying concept of space, the box or arena in which the earth and the spheres are placed. To modern ears, this picture of the universe consisting of a fixed earth and a set of spinning spheres sounds rather quaint. To find the flaw in Aristotle's answer, let us accept his picture for a moment and see where it leads. According to Aristotle, we should fill space with imaginary grid lines centered on Earth and work out where everything else is and who is doing the moving. If we accept this picture of space as a box filled with objects with the Earth fixed at its center, then it is obvious that you, the passenger on the plane, have changed your position in the box, while the person watching you fly by is standing still on the surface of the earth, hanging motionless in space. In other words, there is such a thing as absolute motion, and therefore absolute space. An object is in absolute motion if it changes its position in space as measured against the imaginary grid which was fixed to the center of the earth. So, a problem with this picture, of course, is that the earth is actually not fixed at all. The earth is actually moving in space. It is a spinning ball in orbit around the sun. In fact, the earth is moving at a fantastic speed of 67,000 miles per hour relative to the sun. If you go to bed at night and sleep for 8 hours, you will have traveled over 500,000 miles by the time you wake up. You could even claim that in about 365 days, your bedroom would have returned to exactly the same point in space since the Earth would have created one full orbit around the sun. You might therefore decide to change your picture a little while keeping the spirit of Aristotle's view intact. Why not center the grid on the sun? Earlier, we thought that the earth was fixed and the earth was the center of my grid. Now we can just change it a little bit and center the grid on the sun. It's a simple enough thought, but it is wrong too, because the sun itself is in orbit around the center of the Milky Way galaxy. The Milky Way is our local island of over 200,000 million suns. And as you can probably imagine, it is very large and takes quite a while to get around. The sun, with the earth with it, is traveling around the Milky Way at 486,000 miles per hour at a distance of 156,000 trillion miles from the center. At this speed, it takes 226 million years to complete one orbit. And so, perhaps one more step might be sufficient to save Aristotle. We can center our grid at the center of our Milky Way galaxy, right? And you could have another very beautiful thought As you lie in your bed, imagine what the world looked like the last time the earth was here at this very point in space. It might have been 226 million years ago while the earth and the sun were going around the Milky Way. Basically, dinosaurs would have been alive when the last time you were at this very point in space with reference to our Milky Way galaxy center. However, this notion is also wrong. In fact, the galaxies themselves are not fixed and they are racing away from each other. And the more distant the galaxy, the faster it recedes from us. So, so Aristotle has a problem because it seems to be impossible to define exactly what is meant by the words standing still. In other words, it seems impossible to work out where to center the imaginary grid against which we can work out where things are and therefore decide what is standing still and what is moving. This constantly shifting view of the position of the earth, the planets, and their motion through the heavens should serve as a lesson to anyone who is absolutely convinced that they know something. There are many things about the world that appear at first sight to be self evidently true, and one of them is that we are standing still. Future observations can always surprise us, and they often do. Perhaps we should not be too surprised that nature sometimes appears counterintuitive to a tribe of observant, carbon based ape descendants roaming around the surface of a rocky world, orbiting an unremarkable middle aged star at the outer edge of the Milky Way galaxy. Galileo Galilei was born 20 years after Copernicus proposed his sun centered model of the universe. And he thought very deeply about the meaning of motion. His intuition would probably have been the same as ours. The earth feels to us as though it is standing still, although the evidence from the motion of the planets across the sky points very strongly to the fact that it is not actually standing still. Galileo's great insight was to draw a profound conclusion from this seeming paradox. It feels like we are standing still, even though we know we are moving in orbit around the sun. Because there is no way, not even in principle, of deciding what is standing still and what is moving. In other words, it only ever makes sense to speak of motion relative to something else. This is an incredibly important idea. It might seem obvious in some sense, but to fully appreciate its content requires some thought. It might seem obvious because clearly, when you sit on the plane with your book, the book is not in motion relative to you. If you put it down on the table in front of you, it stays a fixed distance from you. And of course, from the point of view of someone on the ground, the book moves through the air along with the aircraft. So it seems obvious. However, the real content of Galileo's insight is that these statements are the only ones that can be made. And if all you can do is speak of how the book moves relative to you as you sit in your aircraft seat, or relative to the ground, or relative to the sun, or relative to the Milky Way, but always relative to something, then absolute motion is a redundant concept. Let's say that we want to establish whether Aristotle's grid, which would allow us to judge whether something is in absolute motion, is useful from a scientific perspective. Useful in a scientific sense means that the idea has observable consequences. That means it has some kind of effect that can be detected by carrying out an experiment. By experiment, we mean any measurement of anything at all. The swing of a pendulum, the color of light emitted by a burning candle flame, the collisions of subatomic particles in the collider at CERN. If there are no observable consequences of an idea, then the idea is not necessary to understand the workings of the universe, although it might make us feel better. This is a very powerful way of figuring out what is a scientific concept and what is just an opinion. Likewise, the idea of absolute motion will mean something in a scientific context only if we can devise an experiment to detect it. For example, we could set up a physics lab in an aircraft and carry out high precision measurements on every conceivable physical phenomena in a valiant attempt to detect our movement. We could swing a pendulum and measure the time it takes to tick. We could conduct electrical experiments with batteries and generators or motors, and we could watch nuclear reactions take place and make measurements on the emitted radiation. In principle, with a big enough aircraft, we could carry out pretty much any and every experiment that has ever been conducted in human history. The key point that underpins this entire theory and forms one of the very cornerstones of physics is that provided the aircraft is not accelerating or decelerating, none of these experiments will reveal that we are in motion. Even looking out the window doesn't tell us this, because it is equally correct to say that the ground is flying past beneath us at 600 kilometers per hour and that we are standing still. The best we can do is to say that we are stationary relative to the aircraft or we are moving relative to the ground. This is Galileo's principle of relativity, that there is no such thing as absolute motion because it cannot be detected experimentally. This probably won't come as much of a shock to you because we really do know it already at an intuitive level. A good example is the experience of sitting on a stationary train as the train on the next platform slowly pulls out of the station. For a split second, it feels like we are the ones doing the moving. We find it difficult to detect absolute motion because there is no such thing. So, what conclusion about space can be drawn from Galileo's reasoning? The conclusion is this: if it is in principle impossible to detect absolute motion, it follows that there is no value to the concept of a special grid that defines what is at rest, and therefore there is no value in the concept of absolute space. This is important. So let us investigate in a little more detail. We have already established that if it were possible to define a special Aristotelian grid covering the whole universe, then motion relative to that grid could be defined as absolute. We have also argued that since it is not possible to design an experiment that can tell us whether we are in motion, we should abandon the idea of that grid simply because we can never work out to what it should be fixed. Should we fix the grid to a stationary Earth, or should we fix it to the sun, or should we fix it to the galaxy? None of them seems to work because actually we cannot figure out whether we are in motion or whether we are stationary, right? But how then should we define the absolute position of an object? In other words, where are we in the universe? Without the notion of Aristotle's special grid, these questions have no scientific meaning. All we can speak of are the relative positions of the objects. There is therefore no way of specifying absolute positions in space, and that is what we mean when we assert that the notion of absolute space itself has no meaning. Thinking of the universe as a giant box within which things move around is a concept that is not required by experiment. We cannot overemphasize how important this piece of reasoning is. The great physicist Richard Feynman once said that no matter how beautiful your theory, No matter how clever you are or what your name is, if it disagrees with experiment, it's wrong. In this statement is the key to science. Turning this statement around, if a concept is not testable by experiment, then we have no way of telling whether it's right or wrong, and it simply doesn't matter either way. Of course, that means we could still assume that an idea holds true even if it is not testable, but the danger is that in so doing, we run the risk of hindering future progress because we are holding on to an unnecessary idea or a prejudice. So, without any possible means to identify a special grid, we are free from the notion of absolute space, just as we have been freed from the concept of absolute motion. So, what? Well, being freed from the idea of absolute space played a crucial role in allowing Einstein to develop his theory of space and time. But this will have to wait until the next episode. So far, we have discussed in some detail the connection between motion and space. What about time, though? Motion is actually expressed as speed, and speed can be measured in kilometers per hour, that is, distance traveled through space in a particular interval of time. In that indirect way, the notion of time has in fact already entered into our thinking. Is there anything else that we can say about time? Is there some experiment we can do to prove that time is absolute? Or should we also abandon this even more deeply held idea? Although Galileo dispensed with the notion of absolute space, his reasoning has nothing at all to teach us about absolute time. According to Galileo, time is immutable. Immutable time means that it is possible to imagine perfect little clocks, all synchronized to show the same time, ticking away at every point of the universe. One clock could be on a plane, one on the ground, one on the surface of the sun, one in orbit around a distant galaxy. And provided they are perfect timekeepers, they will read the same time as each other now and forever. Astonishingly, this seemingly obvious assumption turns out to be in direct contradiction with Galileo's statement that no experiment can tell us whether we are in absolute motion. Unbelievable as it may seem, the experimental evidence that finally destroyed the notion of absolute time emerged from the type of experiments many of us remember from school physics classes: batteries, wires, motors, and generators. Basically, we will have to reject the idea of absolute time, and time also becomes a relative concept. To address the notion of absolute time, we must first take a detour into the 19th century. We will get into the golden age of discovery for electricity and magnetism. However, that is a topic that we will cover in a future episode. So stay tuned for more physics stories. I'll see you next time.